Okay, guys, here we go. Lecture 2 in week 7, or topic 7. And we talked about your medium temperature lab and the term paper in lecture 1. But now we want to look at your ground source. Ground source.
Hi, I'm Ed Begley Jr., and I'd like to tell you about an exciting new renewable energy technology. Altarock Energy is conducting the Newberry Volcano Enhanced Geothermal Systems demonstration in the Deschutes National Forest in Central Oregon. First, I'd like to tell you a little about the history of geothermal energy and how this new technology, enhanced geothermal systems, can dramatically...
All right, let's get back into that ground source Newberry project. Here we go. EGS, Enhanced Geothermal Systems.
I'd like to tell you a little about the history of geothermal energy and how this new technology, enhanced geothermal systems, can dramatically increase the use of geothermal energy and help secure our nation's energy independence. Geothermal energy, the Earth's own heat, could help solve today's energy challenges. Geothermal power generation dates back to 1904, when at the Larderello geothermal field in Italy, electricity was generated from geothermal energy for the first time. Geothermal energy is already being used today for domestic heating and electricity production, providing clean, renewable baseload power. It could contribute to a sustainable energy future for the United States and around the world. Geothermal power represents an essentially unlimited resource. We can more fully develop and dynamically change our energy future. So what do we need to do to take advantage of this tremendous resource potential? Naturally occurring geothermal systems, called hydrothermal reservoirs, are only found where heat and open fractures filled with water can be accessed at relatively shallow depths, like in the western U.S. and around the Ring of Fire. What if we could create ideal geothermal conditions almost anywhere? That's exactly what Enhanced Geothermal Systems, or EGS, proposes to do. To help us fully understand EGS, let's first look at how a natural hydrothermal system works. In a naturally occurring hydrothermal system, groundwater is heated by underlying magma or by circulation through deep faults or fissures. Production wells, drilled into the Earth's surface, tap into the hot fluid of these naturally occurring hydrothermal reservoirs. Under pressure, heated fluid flows up these production wells to the surface and into a power plant. Geothermal energy gives us a reliable flow of renewable baseload power with minimal environmental impact. Remember though, naturally occurring geothermal does have its limitations. It can only be used where underground reservoirs naturally exist, mostly in the western United States. EGS, however, can be created almost anywhere. By creating a water-filled fracture network in hot rock, we can make a geothermal reservoir. EGS could be a viable solution to the energy challenges facing us today and to the creation of a new energy economy. Let's look at a current EGS project, the Newberry EGS demonstration being conducted by Altarock in the Deschutes National Forest in Central Oregon. In Phase 1, a team of scientists and engineers review existing data about the Newberry EGS demonstration site, conduct baseline measurements, develop plans, and obtain permits for Phase 2 operations. In Phase 2, we will create an EGS reservoir around an existing well, over 10,000 feet deep, using Altarock's proprietary methods and technology. By injecting water at high pressure, we will open or stimulate existing natural fractures using a process called hydro-shearing. Clean, cold groundwater, produced from an existing on-site shallow water well, is pumped at high pressure deep into the injection well, where the temperature is over 600 degrees Fahrenheit. When the cold water reaches a hot, dry rock surrounding the well bore, the injection pressure causes the existing natural fractures to open and fill with water. This process is continued until cracks are opened to a distance of about 1,500 feet, or 500 meters, around the well bore. When the first fracture system has grown to the desired size, a biodegradable, non-toxic material called a diverter is injected with the water to temporarily block fluid flow into the newly opened fractures. The diverter forms a shield around the well bore in the first set of fractures, so more fractures can be opened deeper in the well bore. As the diverter begins to block the first set of fractures, continued water injection causes a second fracture system to open, followed by a second injection of diverter, shielding the second fracture system from further stimulation. We use this to control the size of the reservoir as it forms. A third cold water injection creates the final fracture system, and the stimulation process is complete. At this point, the water injection is stopped and the injected water begins to reheat. As the water heats, the biodegradable diverter begins to dissolve, allowing the fractures to open and the water to flow through the entire fracture network. The hydroshearing process and opening of cracks creates movement and sound in the rock, resulting in microseismicity. The opening and growth of fractures during stimulation is mapped by real-time measurement of this microseismicity. Using a microseismic array and AltaStim, AltaRock's sophisticated proprietary modeling software, we can closely monitor the process. We'll map the fracture network and generate a microseismic event map around the well bore, showing us the size, location, and orientation of the fracture system. With all this information, we know where to drill the production wells into the fracture network. Conventional well drilling techniques are used to directionally drill production wells into the newly created EGS reservoir. Precision-guided directional drilling allows us to penetrate the greatest number of open fractures for maximum well productivity. Cold water can now be pumped down the injection well, flowing through the newly created EGS fracture network, absorbing heat and flowing up and out of the production wells, creating hot water or steam to generate electricity or provide domestic heating. In Phase 3 of the Newberry EGS demonstration, we summarize the collected information to develop a conceptual model of a commercial-scale EGS system, including the most cost-effective way to create an EGS reservoir, the performance that can be expected, the number of wells required, and the best type of power generation technology to use, either flash or binary. While not part of the Newberry EGS demonstration, electricity can be generated from geothermal energy using one of two power cycles, flash or binary. In a flash system, steam is separated from hot water in a pressurized vessel. In a binary system, the hot water is used to boil a working fluid, often isopentane. In both systems, the heated fluid is then used to turn the turbine and generator. Flash systems typically use wet cooling systems that consume relatively large amounts of fresh water, while binary systems often use air cooling, which consume no water and have low visual impact. In either system, any remaining liquid is recycled back into the geothermal reservoir. The steam in a flash system, or working fluid in a binary system, turns the generator, producing electricity that is delivered to the national electric grid and on to consumers. EGS is a renewable process that's environmentally friendly, generates tax revenue and family wage jobs at home, and will help to ensure our national energy independence. EGS, the future of geothermal energy.
There you have it, the Enhanced Geothermal Systems, or EGS. It's going to be on your quiz, huh? So now if we take this to a smaller scale, to the household residential applications.
Geothermal heating and cooling works by tapping into the constant heat source that is found 5 feet below the Earth's surface. In the Northeast, this temperature is approximately 53 degrees. Direct exchange geothermal, or DX, outperforms water source geothermal systems by 25% and is the most efficient system on the market. That's because DX does not require electrical circulators, which use additional electricity. DX only requires one heat transfer, and DX utilizes copper piping, which has superior heat transfer properties instead of the plastic tubing used in water-based systems. Our equipment and installation are wet conditions, which are preferred for conductivity. Each borehole is drilled vertically and is spaced 7 feet apart. This prevents the phenomenon of ground loop interference. Envision each borehole as a 7-foot diameter cylinder that uses this area to gather the Earth's energy. When ground space is a concern, a teepee style or slant configuration can be used to reduce the area needed for drilling. Notice the reduced surface area needed at the top of the boreholes. Here's a simplified version of how a heat pump works when heating your home. All heat pumps have a compressor and an expansion valve that manipulate refrigerant. A refrigerant has 2 phases, gaseous and liquid. Refrigerant works on the basic principle that if you raise the pressure, you raise the temperature. If you lower the pressure, you lower the temperature. This is all done with a compressor and an expansion valve. Let's say the refrigerant starts its journey in its gaseous state and enters the compressor at 30 degrees. The compressor compresses the gas, which increases the pressure and raises the temperature to 160 degrees. The refrigerant travels to a coil where a fan blows across it. The air blowing across this coil absorbs the heat energy and distributes it throughout the home. As the refrigerant leaves the coil, it condenses back to its liquid state and moves toward the expansion valve at 85 degrees. The expansion valve is basically like a dam with a small hole. When the refrigerant passes through the expansion valve, the pressure rapidly decreases and the temperature falls to 20 degrees. It then moves toward the TXV valves. These valves control the amount of refrigerant distributed to each ground loop. The refrigerant is then piped out to the well field and down the vertical boreholes where it begins its transformation back to a gas. As it transitions back to its gaseous state, it absorbs heat energy from the Earth and travels back to the compressor where this ingenious process is repeated. When cooling is desired, this process is reversed.
So you see here where 20 degrees in this for the heating I did 10 degree differential, 20 degrees after the expansion valve, and then when it comes out of the Earth it's up to 30 degrees. So it's been designed such that for this size of home and this length of pipe for a 10 degree temperature differential. But let's look at the cooling aspect.
What if there was a way to heat your home in winter, cool it in summer, and provide abundant hot water all year round, all while cutting your utility bills by up to 80%? How? By installing a Climate Master geothermal central heating and air conditioning system in your home. Here's how it works. Wherever you live, the temperature beneath your home remains constant regardless of the season. Just a few feet down, the Earth has a consistent 55 degrees. Summer or winter. Climate Master geothermal heat pump systems harness this stable underground temperature to provide heating, cooling, and hot water at remarkably high efficiencies. So high, in fact, that energy use can be cut by up to 80%. To access this stable underground temperature, a geothermal heat pump is connected to a series of underground loop pipes. These loop pipes are made from an extremely strong and long-lasting material. Water, usually mixed with an environmentally safe antifreeze solution, is pumped through this loop pipe system. In summer, the heat pump takes heat from the air in your home, transfers it to the underground loop system, which then radiates the heat away into the cool earth. Now cooled to a comfortable temperature, the air is circulated through your home using a traditional duct system. In winter, the system is reversed. Heat is extracted from the ground using the same loop system. In the heat pump, the heat from the underground loop is compressed to a much higher temperature and used to warm the air in your home. Since a geothermal system uses an earth loop to provide your home with heat in the winter, there is no need to burn any fossil fuel for heating. No flame, no carbon monoxide, and environmentally friendly. Geothermal systems are the smart way to heat and cool your home. Let's compare a high-efficiency gas furnace to a geothermal system for heating your home. A high-efficiency gas furnace will give you less than 0.96 units of heat for each unit of gas burned. In contrast, A geothermal system gives you up to 5 units of heat for each unit of electricity used. How can that be? A furnace makes heat by burning fossil fuel. A geothermal system doesn't make its own heat. It simply collects heat from the earth and moves it to your home. Now let's compare a geothermal heating and cooling system to an air source heat pump for cooling. When it's hot outside, an air source heat pump takes heat from your home and moves it to the outside air. As the outside air becomes warmer in summer, it becomes harder and harder for the system to dump heat from your home into the already hot outside air. Because of this, when cooling a home with an air source heat pump, the system becomes least efficient when it needs to be most efficient. A geothermal heat pump system doesn't have this problem. A geothermal system exchanges the heat in your home with a cooler ground using its underground loop system. It simply doesn't have to deal with high outside air temperatures the way an air source heat pump does. Add to this the fact that a geothermal system is installed safely inside your home with the loop buried underground. Unlike an air source heat pump, there is no outdoor equipment exposed to the elements or the risk of vandalism. Let's take a look at geothermal loop systems. There are several different ways to install a geothermal loop system. Where space allows, horizontal loops are the most cost-effective loop design for most homeowners. If space is limited, a vertical loop system is often the best choice. If a nearby pond or lake is available, a coiled loop system can be used. This is the fastest, easiest loop system to install. If a well is available that produces sufficient volumes of water, an open loop system can be installed. An open loop system takes water from the well, pumps it through the heat pump system, and then returns it to the environment in a responsible, renewable manner. And geothermal systems don't just heat and cool your home. They can also provide you with hot water. Besides a nice shower and washing your hands, you can use the large volumes of hot water a geothermal system can produce for radiant underfloor heating, or even for snow and ice melt under your walkways and driveway. A geothermal central heating and air conditioning system from ClimateMaster can be installed in almost any home, new or existing. They can be installed in an attic, garage, or utility closet. Or, in the case of a retrofit installation, they can even be installed in place of an old outdoor air conditioning compressor section. There are even more ways to save with a ClimateMaster geothermal system than just lowering your utility bills. You can save up to 30% off the total cost of installing a ClimateMaster geothermal system with a federal tax credit. Additionally, many states and local governments and utilities also offer incentives for installing a geothermal system. As the world's largest and most progressive leader in clean, renewable geothermal technology, for more than 50 years, ClimateMaster has designed and manufactured industry-leading heating and cooling equipment for the commercial and residential construction market worldwide. Visit us at climatemaster.com to learn more about geothermal central heating and air conditioning systems.
ClimateMaster, there's somebody to check into, huh? And these underfloor, we're going to look at these later. So we'll hold off on this for now.